Welcome to the first lesson of a topic titled Exponential and Logistic Modeling. In this lesson, we'll discuss exponential models, bacteria growth, and logistic models. Let's start with the exponential model that was introduced in topic 1. F of x equals a times b to the x. The initial value of that function is a. When x equals 0, b to the 0 is 1, times a is a. And the number that tells us how quickly that exponential model grows is b. When b is large, that exponential model grows quickly. So b is like a rate. So let's understand b as a rate in the context of a population growing. We have a new model, p of t equals p sub 0 times 1 plus r to the t. P sub 0 is the initial population. 1 plus r is b, therefore r is the rate of growth of the population, and t is time. In the left column, let's play around with that model a little bit. On the left, we have time. On the right, we have population. And let's plug in 0, 1, 2, and t. When we plug in time equals 0, we should get the initial population. So let's try it out. P sub 0 times 1 plus r to the 0. Interesting. 1 plus r to the 0 is 1, and that gives us p sub 0. Suppose time equals 1, such as 1 year. We plug in 1, and we get p sub 0 times 1 plus r. We've taken our initial population and multiplied it by 1 plus the rate of growth. Think about what would happen if r was 0. We would just multiply the initial population by 1, and we could do that over and over, and we'd have the same population. Then we could plug in 2, 3, 4, and so on, all the way up to t, and we get our population model based on time. What if we had the model and we wanted to find out what the rate was? Notice the second column. And notice how 1 plus r is combined into the number 1.021. So we have the initial value, 786,543, and our goal is to simply find the rate. So we'll set 1 plus r equal to 1.021 and solve for r. R is equal to 0.021, and if we multiply by 100, we'll get a percentage, which is 2.1%. And that's a growth rate, but if the base of this function was less than 1, then it would be considered a decay rate. The population is decreasing. And if it was 0.79, it'd be decreasing by 21%. Let's say you know some information about your population and you're trying to find a function that models that situation. Check out the right column. The initial value is 10, and the population is increasing 5% per year. Well, that means p sub 0, the initial population value, is 10. R is equal to 0.05, 5% as a decimal. And the model would be p of t equals 10 times 1.05 raised to the t. Once again, anytime we see a base that's bigger than 1, it's a growth model. Speaking of a growth model, let's talk about bacterial growth. We'll leave radioactive decay for another time. Suppose a culture of 200 bacteria is put into a petri dish, and the culture doubles every hour. 200 exactly. Predict when the number of bacteria will be 350,000. As we underline helpful information in this example, let's think about how we would start the prediction process. 200 bacteria, that's helpful. Doubles every hour, that's helpful. And 350,000. That's what we're shooting for. From my perspective, there are two approaches to this problem: playing with numbers and working with a model. So let's play with numbers first. I'm setting up a table that includes time in hours and population of the bacteria. I'm interested in what the population is at time equals 0, 1, 2, and 3, just to see how quickly the population grows. At time equals 0, the population was 200. That was given. By the time 1 hour passes, the population doubles, so 200 times 2. By the second hour, it doubles again, 200 times 2 times 2. And then by the third hour, the population doubles 3 times, 200 times 2 times 2 times 2. We can keep playing with these numbers until we get to a number that's pretty close to 350,000. But the time at which that happens will not be a whole number. But why? Well, because 350,000 is not a power of 2. So let's create a model. The initial population is 200, and the base is 2. Therefore, our model is P of t equals 200 times 2 to the t. Let's set that model equal to 350,000 and solve. We do that by dividing by 200 and then taking the log base 2 of both sides. But we're not going to use that method right now. We'll go to the calculator. We'll let y1 be the model, 200 times 2 to the t, or 2 to the x, and let y2 be 350,000. By using the intersect feature, we would find that the t value, in which the population is equal to 350,000, is 10.77 hours. Wow. Comparing that number to the population at time equals 3 hours, that is a lot of bacterial growth in just 7.77 hours. The last example I have for you is about how to model a rumor using a logistic model. The logistic model itself is kind of nasty, but the idea is fairly simple. A population, rumor, or virus spreads exponentially at first, but then levels off eventually because there's a maximum sustainable population. There's a limit to the growth. Let's work through this example. Let's say Founders Classical Academy has 150 high school students. 5 students start a rumor, which spreads logistically so that S of t is equal to 150 divided by 1 plus 29 e to the negative 0.9t. I'm giving you that function S of t, S for spreading a rumor, and it models the number of students who have heard the rumor by the end of day t. The denominator of that function shows that there's exponential growth because of the e, and the numerator of that function shows that the population is limited. There's a maximum sustainable population of 150. In other words, the most students who can hear that rumor is 150. So, how many students have heard the rumor by the end of day 0? Well, we already know that it's 5, but let me show you how we could plug in 0 and get 5. Plugging in 0 for t, we get e to the 0, which is 1. 29 times 1 is 29, and if we add that to 1 in the denominator, you get 30. 150 divided by 30 is 5. Part B is a little more challenging. How long does it take for, 75 students to hear the rumor? Half of the population. Well, just like the previous example, we need to set our model equal to the value that we're looking for and solve using technology. So in this case, we'll let y1 be this function and let y2 be 75, and then find the intersect of those two functions. You'll have to change the window a bit. I set my ymax to be 200 so I could see the entire function, and I let my xmax be 30. I found that it takes 3.74 days for 75 students to hear the rumor. So 3 days and 3/4 of the way through the 4th day. And that is the end of lesson 2. Thanks for watching. I'm Mr. Stark. Join me for the next lesson on exponential and logarithmic functions.